So now that we are getting kind of comfortable, hopefully, working with these trigonometric functions, let's try to use them for something. So we're going to build a gutter. And what we do is we take a 12-inch wide sheet of aluminum, and then we bend it at equally spaced points. So we have 4-inch, 4-inch, 4-inch. And then at this point and this point, we just bend it up. And now I have a little gutter. Okay? I'm going to bend both sides up the same angle, where that angle is theta. Okay. Now, later on we can figure out where this formula comes from, but for now let's just believe the manufacturer that the area is given by 16 times the sine of theta times, in parentheses, cosine of theta plus 1. Okay. So for 3 different choices of the angle to bend, find the area of the opening. Notice sine and cosine of these angles we have in charts. So you can flip open to a book or just open like a reference on your phone or something. These are values for which we know sine and cosine. So honestly, all you have to do is plug them in. So go ahead and do that, and then we'll double check on the next slide. Okay. So if you plug in 30 degrees, we know the sine of 30 degrees is a half, and the cosine of 30 degrees is root 3 over 2. If you start distributing out your 16 across all these fractions, it's approximately 14.93 square inches, assuming this was measured in inches. It was, okay. For 45 degrees, the sine of 45 degrees is root 2 over 2, and the cosine of 45 degrees is also root 2 over 2. So we end up with a bit more, 19.31 square inches. What about 60 degrees? Well, the sine of 60 degrees is root 3 over 2, and the cosine is 1/2, and that works out to be even bigger, 20.78. Okay, so this was just a matter of computing some things with a formula. Where that formula comes from, we can answer later on in the semester. And if you then ask, well, what about, so here was the relevant picture. Okay. How would I determine the angle to make this area as big as possible? Because you can kind of imagine if theta is really small, I have very little area, I have very little space for the water to flow through. But if I make theta too big, maybe I even bend it inwards. Now I have, so now my theta is like all the way to here. I have a pretty bad gutter that way as well. Somewhere in between, there should be an opening, or sorry, an angle theta that makes the biggest possible area. And since that's where the water is flowing, that makes a gutter that can carry the most water possible. So can you find that angle that maximizes the relevant area according to that formula? And yeah, you can do it in Calc 1. You'll learn how to solve that kind of problem. Okay, so what we've done so far is we've got reference angles that we know sine, cosine, etc. for 0, pi over 2, pi, 3 pi over 2, pi over 4, pi over 6, and pi over 3. Now we're going to exploit some symmetry to get a whole bunch of other things automatically filled in for us. So for example, we've determined in that box off to the right, the cosine and sine of pi over 4 are root 2 over 2 and root 2 over 2. But now, based on symmetry of the circle, if I took this point and I reflect it down, I didn't change the x-coordinate, but I did change the y-coordinate. I made it negative. But what angle would that be? Well, instead of this angle here, I moved it down here, which corresponds to that angle all the way around, or 7 pi over 4. So now, for example, we can say the cosine of 7 pi over 4 is root 2 over 2. And the sine of 7 pi over 4 is negative root 2 over 2. Just based on a symmetry argument using a point we already knew. Similarly, you can reflect this across the y-axis to make the x-coordinate negative and the y-coordinate stays positive, or you can reflect it across the origin to make both of them negative. And that'll give you the sine and cosine of 3 pi over 4 and 5 pi over 4 respectively, allowing us to fill in a whole bunch of sort of entries in a chart without doing much more work. Okay, so work through and try to find all of the following, and then we'll double check. Okay, hopefully you paused and you're back now. So just looking at that reference picture on the previous slide, The negative root 2 over 2 comma negative root 2 over 2 corresponds to the angle 5 pi over 4, so the sine is the y-coordinate, which is negative root 2 over 2. 135 degrees you convert to radians and you would get 3 pi over 4, or you could call it 90 degrees plus 45 degrees and just sort of figure it out. The point negative root 2 over 2 comma positive root 2 over 2. We were asked for the cosine, and that's the x-coordinate, which was also negative root 2 over 2. 315 degrees is 7 pi over 4. X is positive root 2 over 2. Y is negative root 2 over 2. We were asked for the cotangent, so we take the ratio of x over y and get negative 1. Root 2 over 2 comma negative root 2 over 2 corresponds to an angle of negative pi over 4. So negative pi over 4 was not in that chart, but it just means instead of doing pi over 4, do the same angle, but in the clockwise direction. And you ended up at that point down there. And we were asked for the cosine, which was positive root 2 over 2. And finally, 11 pi over 4. This is actually bigger than 2 pi. So 11 pi over 4 is 8 pi over 4 plus 3 pi over 4. And this is just 2 pi. So that says go all the way around and then do 3 pi over 4. And you get to this point here. We were asked for the sine, which is the y-coordinate, which was positive root 2 over 2. Okay, we can do similar tricks with our 30 degree and 60 degree, or pi over 6 and pi over 3 points. We perform various reflections to fill in different angles there as well. Okay, so either by opening this on another screen or on your phone, or by flipping to a page in a physical book, if you have it, can you find all of the following: cosine of 210, sine of negative 60 degrees, tan of 5 pi over 3 radians, cosine of 8 pi over 3 radians. Okay, notice this just means rotate clockwise, and 8 pi over 3 is 6 pi over 3 plus 2 pi over 3, which is a full rotation, and then 2 pi over 3. Okay, so work through these, and then we'll check. Okay, so converting 210 into radians, we get 7 pi over 6. How would you know that the cosine of this is negative root 3 over 2? Let me clear out my pen mark so that I have a bit more blank space to work with. So 7 pi over 6, here's how I'd do it. This is pi plus pi over 6. It's a full 6 pi over, or a full pi, plus a single pi over 6. So in my unit circle, I'm going to go all the way to pi, and then I'm going to do pi over 6. So now I know I have a 30, 60, 90 triangle, but pointed in this direction. Okay, if I draw this altitude here, I have that triangle. So it's a 30, 60, 90 pointed in that direction. So here's pi over 6, here's pi over 3. We get used to working with our standard reference triangles. I know this is going to be a half, this is 1, and this is root 3 over 2. But since I am pointed in that direction, this is to the left and this is down, so these should both be negatives. So this point has coordinates negative root 3 over 2, comma, negative 1/2. And then we are asked for the cosine, that is the x-coordinate, which we just determined is negative root 3 over 2. So using similar tricks, if you haven't already, go ahead and complete parts B, C, and D. Pause the video here, come back, and we'll check our answers. Okay, so if we convert negative 60 degrees to radians, we get negative pi over 3 radians. That just means take your pi over 3 angle, but move clockwise, and that has a y-coordinate of negative root 3 over 2. For 5 pi over 3, this is pi plus 2 pi over 3. Alternately, it's pi, it's 2 pi minus pi over 3. So you could find this point by saying go all the way around, but then take away pi over 3 and see where that triangle fits. The y-coordinate is negative root 3 over 2, and the x-coordinate is positive 1/2. Let me clear out my pen marks so that we can see the rest of the work, which simplifies down to negative root 3. And for 8 pi over 3, remember the hint we gave, that's a full 2 pi plus 2 pi over 3. So you can just take the cosine of 2 pi over 3, and that's negative 1/2. Now, for angles other than these quadrantal angles and our 30, 45, 60 degree, aka pi over 6, pi over 4, pi over 3, plus their quadrant rotations, we basically have to use a calculator. We'll learn some stuff later on to get some other values, but for the most part, if you just start throwing stuff into sines and tangents and whatever, you need a calculator to get something you can work with. So just plug them into the calculator. Now, be careful with a calculator, because this is measured in degrees, this is measured in degrees, this is measured in radians. If you have a TI calculator, somewhere buried in the, I think it's a mode button, in a settings button, there's something called mode, and your two options are degrees and radians. So if, for example, you say sine of 48 and you're in radians mode, you will not get the correct answer here. If you say tan of pi over 14 and you're in degrees mode, you won't get the answer here. So if you need to go back and forth between degree and radian measurement, just make sure you're changing the mode on your calculator. If you're working on a desktop, okay, you can use Google. Now, it's worth pointing out, by the way, you're allowed to use certain pre-approved calculators on exams. You can't use Google on exams, I think, for obvious reasons. Okay, so if you are relying on a desktop computer to do your basic calculator functions, get used to not using it when it comes to an exam. In Google, if you just typed sine of 48, it's going to assume you meant radians. If you want to do degrees, you can just type sine of 48 and then just write degrees, and it'll compute it for you. It understands what that means. Okay. Anyway, go ahead and compute these. Honestly, we're just checking that you can properly use your calculator, including changing between modes. So in degrees mode, sine of 48 is about 0.74. Most calculators do not have a secant button. Some do, I'll admit. If you don't, that's fine, because remember, secant is 1 over the x-coordinate. That's 1 over cosine. So to find the value of secant of 21, you can just find cosine and do 1 over that, and you should get 1.07. Okay. For the last one, notice this one is in radians, so make sure to change to radians mode if relevant, and tangent, usually there is a tangent button. If there wasn't, you can just do the sine divided by the cosine, and you'd get 0.23. Okay, so make sure that you know how to use your calculator if you're going to be using it. Okay. Not all circles are unit circles. Sometimes I might have a circle still centered at the origin, but the radius is bigger. Okay. You can still compute, you have a big circle, now the radius is r. If you mark off an angle of theta, I still have an x and a y here. Since I'm no longer in the unit circle, this is not necessarily the cosine and sine, because the unit circle might be smaller or bigger, making x, y somewhere else. But in a circle of radius r, I still have a point here. And you can still work with your trigonometric functions. Okay? It's now, the only thing that changes is you consistently have to divide by the radius. So the sine of the angle isn't just y, it's y over the radius. This is frequently written as the y-coordinate of that point is r times the sine of theta. Similarly, the x-coordinate is r times the cosine of theta. Tangent is still the sine of theta over the cosine of theta. Now the sine of theta was y over r, and the cosine of it was x over r, and these r's cancel anyway, so this is still just y over x. Similarly, in cotangent, they're going to cancel, and you get x over y. But otherwise, cosecant is 1 over sine, so instead of y over r, you get r over y. Secant is 1 over cosine, so instead of x over r, you get r over x. In other words, if you're using a circle whose radius is 1, you can still work with these functions. You just have to remember to account for that radius. Okay. So find the exact value of each of the 6 trigonometric functions. If the angle is theta, measured in radians, if 4, -3 is a point on the circle. Okay, this is definitely not on the unit circle. 4, -3 will be, say, about here. Okay. So here's my angle theta. Remember, we start from the positive x-axis direction and go counterclockwise. So what is sine, cosine, etc.? We're not on the unit circle, which means your first step is to find r. Well, what is r? It's the distance to the origin of any point on the circle. and we have a point on the circle. So if we find the distance to the origin of that point, found r, and then you can use everything on the previous slide. So there's my hint. Pause here, work through it, and then we'll see the answer. Okay, so since 4, -3 is on the circle, we find the radius by using the distance formula, which gives us a radius of exactly 5. Convenient. Now I can use the previous slide's formulas to say, now that I know the radius is 5 and we know the x and y coordinates, they're 4 and -3 respectively, the sine of theta is y over r, -3/5. The cosine of theta is x over r, +4/5, etc., 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 etc. Once you know the x and the y and the r, all of this falls into place. The real work of this problem was just finding r. Since we knew a point on the circle, that's just the distance formula. Okay, so hopefully we got all that. So that's the end of this section, section 6.2. So come on back when you're ready and you have worked through some of the homework problems from this section. We'll move on to section 6.3. Who would have guessed?